section for programming an FRC robot. So in the robot, and I don't want to keep switching the VGA cable, so I'm gonna go off of this now. So understanding robot main. This is what I was showing you earlier. Again, how this is forcing data flow. These VIs right inside of this, and what this is that same sequence structure that I was showing you before, except there's only one frame. And they're forcing data flow by having the error cluster go to that sequence structure, except nothing inside of the structure is using that data. Okay. So robot main, you'll get a project in Labview that looks like this. Robot main is the main, it's the main. I mean, you know, in normal programming, you have a set of code, a module, or something that's going to run as soon as you start the program, and you set that up in your setup. Begin. This VI is where you initialize all of your motors and sensors and your joysticks. Usually there's minimal code outside of that. You can set constants there. So what's happening here is, once you come from begin, you're going to enter this loop. And this loop is where your Attendees occurs. It's where your teleop occurs. And there's this case structure right here. Right now it's looking at teleop enabled. It's kind of hard to see, but and then this is the teleop VI. So the way you can get to the teleop VI is either from your robot project, or you can open up the main program and then find it in here. And then if you were to double click on this teleop VI, you could open up teleop and put your logic inside of there.
So if I understand you correctly, that's a VI, but it's openly visible. Or are you just talking about
it's a sub VI. Yeah. Yeah, these are this is a sub VI, this is a sub VI, this is a sub VI, this is a sub VI. This is a reference to a sub VI.
Which is, sorry?
This is a reference to a sub VI. Attendees works a little differently. You have teleop here, and Attendees works a little different. I can bring that up on that computer, but let me just keep going through here. So yeah, so it's showing here. Yeah, these are my sub VIs. This is that sequence structure, my while loop, my case structure. Basically, this is working like that state machine. Okay, except I'm not using a shift register. I am using the robot mode VI, which is actually connected to the FMS station in competitions. So, which is driven from your driver station, right? So the FMS connects to your driver station. Your driver station controls which mode you're in. So when you open up your driver station, oh, okay, you probably didn't install that either yet. You all familiar with the driver station? What that looks like? Okay. So the driver station is where you can select whether you're going to run your Attendees code or your teleop code. In competition, that comes from the field management system, which is the folks that sit on the side and tell you when to start and stop. Okay, the Begin VI, again, this is where you're going to initialize. So here they're showing, let's see, does this zoom in at all? Yeah. So this is how you would initialize your motors. This is saying, okay, I'm going to give it a name and I'm going to call it left and right motors. My right side is inverted. My left motor is working off of PWM number 1, and my right motor is working off of PWM number 2. So this opens those references, and it passes in a cluster all of this data that I just put into this open 2 motors VI. All of that data comes over to this set VI, which is going to set those references to this name, left and right motors. So that in other parts, in other areas of the robot project, you can reference this either by the cluster or by the left and right motors name using a get. So this is a set. This sets it to left and right motors. If you use a get somewhere else in the program, it will get left and right motors. And then what will output is these values. You don't get it? I'll show you. I'll show you in a second. If you remember clusters, remember cluster is a set of controls or indicators of different data types. Okay, and so what I'm setting here, I'm setting PWM 1 and 2 to be left and right motors. So I'm setting it with this VI. I'm opening it with this VI, but then I'm setting it with this VI to this name. And that can be a little tricky because it's case sensitive. So if I were to type, if I set it to left and right motors with capital L, capital R, capital M, but then I go and do a get with all lowercase, I'm not going to retrieve these values because it's case sensitive. You have to use the exact name that you set it to. So yeah, again, this is a pink string refers to the ref num or reference number given to the device. Here it's left and right motors, and will be called later in the program to access the Jaguar speed controllers. And it's a registry set VI. So now in teleop, this is where you would set all of your logic for the teleop program, so that when you begin to run teleop in the match, this is the logic that's going to execute as the logic in your teleop VI. Autonomous independent is, you can access it. Again, this is a reference. I can go back when I bring it up on that other computer and show you. But this is actually going to reference the autonomous independent VI. And again, you have in your robot project, so that list of VIs, that structure, you can, just the same way you added logic to the teleop VI, you can add logic to your autonomous VI. By default, it gives you something like this. By default, this is in the VI, but it's disabled. So there is a way to disable code in Labview. If you go to your structures palette, you can drag a disable across like you do a case structure or a while loop or something like that. It will be disabled so that this does not automatically run if you forget to, if you forget it that it's there. It's there, but it's disabled. So what this is showing is a get right here. So I've set it in Begin, and now I'm doing a get, and I'm using that same name, left and right motors. And what I get out is that cluster that I set in Begin. Okay? And so when I get my left and right motors, now I have access to these drive VIs to be able to utilize the data, those PWM references that I opened in Begin. And so I can say this is using arcade drive, and the inputs are the speeds for the axes that I want to drive. So I have two axes. I have my left and I have my right motors, PWM1 and PWM2. And what I'm doing here is I'm setting the speed on each of those. So this would be PWM1 speed, this would be PWM2 speed. So if my left is driving slower than my right, I'm going to be turning left. So this is a turn left, and I'm going to do that for 20 iterations. Okay? So this while loop, actually, and it's going to run for a second. Can you tell how I figured that out? Anybody? Huh? 20 times 50. My delay is 50, and I'm going to run it 20 times. So I get a second to run and turn to the left. Okay.
Hypothetically, the other actions built into that VI took longer than 50 milliseconds, would the wait just have no effect?
Right. It wouldn't have any effect. Yeah. If this VI executes longer than this 50 milliseconds, then this loop is going to run for longer than 50 milliseconds. It's going to continue to execute this VI. This wait is not going to stop this from executing. Now, if I were to use that time structure, that would change, because then I'm setting the loop to run deterministically at a certain rate. Okay. And so I'm going to turn left, and then once I turn for that second, then I'm going to turn for 1 second, or half a second. Well, I guess this was not 2 seconds. Did I say 2 seconds? It's 1 second. It's 1 second. This is going to turn for 1 second. This is going to turn for half a second to the right. And then this is going to basically stop. So you're going to set your motor values to 0 speed, which is going to stop the motion. So you're going to turn left for a second, turn right for half a second, and then you're going to stop. And it says, keep calling robot drive in the loop to avoid an error. And it's forcing data flow because I'm wiring from this loop to this loop. And then from this loop, this is going to execute, and then I have a wire going from this loop to this loop. If this is not here, you will not, you'll have something bad probably happen. Your robot's probably going to be shaken because it's going to be trying to turn left and right at the same time, because this loop will be running and this loop will be running at the same time. Actually, so will this loop, so you'll be stopping while you're running. That's why data flow is important to get down. That's like the biggest learning curve with Labview, is you can force data flow, and that's how they're doing it here. You could also accomplish this using the sequence structure that I showed you earlier, where instead of having, or you could accomplish the same thing with a state machine, where you could say, using an enum, you could say turn left and execute this same logic, and then you could have, and then once this condition is met, then you change the state that you want to run next to turn right. Okay, this is just the default program that's there, but you can modify it if you want to, because you'll more than likely in Auton be doing more than just turning left and turning right. You want to add more logic to that. Okay, and then there's the finish VI, where you have a begin, where you open your references and assign names to those references, and then you have a finish VI where you close those references because you don't want to leave. That's just gonna take up memory on your CRIO and cause issues later when you go to stop. And that's another thing. When you are running your program in Labview on the computer or on the serial, you really don't want to use this stop button. Okay? For this very reason. If you're pressing this stop button, yes, you're stopping the program from running, but what you're not doing is running this finish VI. So let's say you're running teleop. You've opened the references, you're using the references in teleop, but then you go and hit this stop button. Well, the logic of the program is set to, when you want to stop, there's a stop button, which will then send you to the finish VI so that you can close those references. If you hit that stop button, you're not going to close those references. It's just going to stop where it is. Okay. And so basically for every reference that you open and begin, you want to have a close for it and finish. So you want to do the get, pass it in, and use the close VI for that particular reference device. Okay, so you build all your logic in Labview, and then you have to get it on the robot so that you can test it. You want to build all of your code up into an executable, and then you need to deploy that executable to the serial. Okay. Where is it? So when you create a robot project, you give it a name, you set a location for it, and you set the serial IP address so that you can communicate with it. So you want to make sure that your IP address is on the same subnet as your serial so that you can see it firstly, and then you'll get, when you hit finish, you'll get all of these VIs in that robot project. This is the project Explorer. Here's robot main. Your team code is where your begin and teleop and auton and finish, those VIs are in team code. It's robot main again. Okay, so when you deploy your code, not typically how we do it. This is a little outdated. So under build specifications, you're going to have your setup to build. So when you hit build, you can right click on it, and I'll show you again on the laptop. When you select it, you hit build. It's going to build the executable. If you selected it, right click on it again and hit deploy, it's going to deploy that executable to the serial. And okay. There's another option when you deploy. There's the option to run as startup. And that is so I can deploy code to the robot, and the robot may already have code on it, permanent code. But I can deploy to that robot and run the code so that I can test, but it will not overwrite the permanent code that's already there. There's volatile memory and non-volatile memory on the serial. The volatile memory is the memory that can be overwritten. The non-volatile memory is the memory that is permanent. It's going to stay on the robot so that when you reset your robot, it has access to that robot code that was made permanent. And you make robot code permanent by selecting, again, under the build specifications. This isn't expanded right now, but there's another item under this where you can, again, build your executable and then deploy that executable. But when you right click on it, you can either you can tell it to deploy, and it's just going to deploy to the volatile memory. If you say run as startup, it's going to deploy to the non-volatile memory, and then you'll have to reset your robot to make sure that it runs as permanent code. This is the driver station. This is how you enable and disable your robot. This is where you set teleop and Auton code to run. Again, this is all controlled by the FMS when you are in a match. So you want to set your team number here so that it can communicate with your robot. So if I back up just a little bit here. Here, when you set your serial IP address, the XXYY is going to be your team number. So our team is 1038. It's going to be 10.10.38.02. That's the standard. If your team number is 751, it's going to be 10.07.51.02. This is the diagnostics tab I was mentioning earlier, where if there's something going on with the robot, you can look at the diagnostics tab to find some indicator as to what might be going wrong. It's actually a text box that fills in with errors or warnings. So again, as I mentioned before, your joystick is a cluster. So when you get your joystick, you're going to have, you can either get your axes or you can get your buttons. Your buttons will be a cluster, and then your axes will be a cluster. And then if you unbundle those, then you have access to axis 1, axis 2, axis 3, and then you have access to button 1, button 2, button 3 if you unbundle your buttons. If you look over really quickly, if you look over here, I don't know if you all can see this, but up on our board we've drawn a joystick. Y'all can see it. We've drawn a joystick, and it labels which axes numbers to reference in our program, and also what the button numbers are. So that's how. So the best way to figure that out is to wire an indicator directly to the cluster, and then press the button on the joystick, and it'll highlight where or which button is which. And also, if you move the joystick, you can see which axis is changing value. Okay, every time you add a device, you must initialize or open it in the Begin.vi and give it a name. If a new device, for example a motor or a joystick, was added to Begin, you must also close this device in the finished VI. And the device can be communicated to in teleop or the autonomous sub-VIs. So if I'm adding a servo motor, in this logic, I have my left and right drive motors. My reference is going to the arcade drive VI, but I want to control it with my joystick. So I'm also going to do a get on my joystick, and I'm going to tell it, I'm going to pull out which axes I need to use, and also which button I want to control to be able to give it a certain value. And then I also am using axis 4 for my servo to set the angle. So in this logic, I think there's another slide here. So here, okay, they added a limit switch. They added a new device. So for axis 1 and axis 2, well, see, it's still not showing me what I'm doing with that. But let's say I have a digital input. Let me back up, because I think okay. Oh yeah, okay, so this is just stepping through an exercise where it's telling you to initialize a new limit switch using the digital input, and then modify that tele.vi to read the digital input to monitor if the switch has been pressed, and then ultimately you're going to finish. So here, this true statement is setting the motor values to 0, so it's going to stop when it's in the true statement. I didn't cover this, but this function here is a negate. So if the value that's coming out of my get is a false, but I need it to be true, I can use this negate to change it from a false to a true, and vice versa. If it's a true and I want it to be false, in order to work my logic, then I can use negate to change from a false to a true or a true to a false. Here, they're using a joystick button or a digital input to pass a value to my arcade drive VI. So I get the joystick button, which goes into an OR gate. And the OR gate logic works such that if I have input 1 or input 2, then I get a true value on the output. Well, the false case is what's actually passing the value to the drive. So what's going to happen with this logic is when I press the button, it's actually going to run the true state, which is going to stop the motors because remember it was passing a 0. The true state, or the true case, is passing 0 to the motor, 0 speed. Okay. Again, I recommend everybody going to ni.com/first. You can ask support questions. The forums are monitored by NI employees, and also any other FRC teams. Anybody, it's a community, so anybody can get in there and answer questions, including you all. You can post questions and somebody should be able to get to it for you. This is, again, where I got this presentation from, so you can access other training materials, and of course you can interact with other teams and mentors and other students. Some other things that they included in this PowerPoint is you can go to the web and student corner at ni.com/academic. The Labview fundamentals exam is free on ni.com/academic. So if you want to test your skills in Labview, you can go there. It also says you can get your own copy of Labview Student Edition at that location. And again, the ni.com/first is the first website on National Instruments website. And that's the end of the slideshow. Let me go ahead and bring up Do you need my laptop anymore? Oh, no. I'll get it out of your way then.
Some plug-in.
Thanks. Oh, is that the same thing? 2012.
Tenacious. Tenacious.
Thanks again. No problem. Okay, so when you open up Labview for FRC, this is what it looks like. What you want to do to create your robot project is go to FRC Serial Robot Project. You can also modify your dashboard with Labview. So when you open the driver station,
Hey Ryan, do you have any comments for people on installing the official FRC packs and add-ons from Labview? I just wondered if it was really
yeah. So you get the software in your kit of parts. It's usually a disk. I think 1 year was on a USB drive. And you install it, but that just gives you Labview. In order to get Labview for FRC, you have to install the updates on top of it. So you want to install Labview and then the updates. Okay. And there's the driver station update, there's the Labview update, and then there's the utilities for like your serial imaging tool, and I think the radio configuration tool. So you'll notice so this one has already been modified. So what we did was with our dashboard, we added a big button here to tell us when we were at our set point for our shooter wheel being up to speed. So you can actually modify the dashboard if you open up the dashboard project and modify that. And then what you want to do is go to your C program files, FRC dashboard, and you see we have multiple versions here, but the one that's executing is the one called dashboard.exe. So modify it, name it to dashboard.exe, put it in this folder, and you can run your customized dashboard when you open the driver station. If you click on the FRC Serial Robot Project, New, this is where you name your project and you set your serial IP address. Last year they introduced several different types of projects that you can create. You have the arcade drive, hardware only, Mecanum drive, hardware or simulation. And these simulation projects include code that will allow you to run a simulated robot on the computer. So if you don't have it connected to a robot, you can drive and simulate how your robot will run in the simulator. So, Alexander, do you want to show our code from last year?
Sure.
Does anybody have any other questions right now? Okay. Yeah. Okay.
So, do you have an estimate just for people, if you have Labview installed and you start to download the packages you need for all the FRC code and install them and go through, how long do you think that might take?
Depends on your computer. If you have a i5, i7, shouldn't be more than a half hour. Probably a lot quicker than that, 10 minutes.
Okay. I seem to remember downloading the patches and getting them all right.
Yeah.
Quite a few hours. So.
Yeah. Well, it can take a while, but I've seen it run really quickly. So it sort of depends. They've improved it over the years. In fact, we're doing the beta. We're a beta test team for next year's Labview 2014, and typically with Labview, you have several updates that you have to install. Again, the Labview update, the Driver Station update, and the utilities. This upcoming season, they will all be packaged into one update. So they're working to improve it, but you know, and they've said that they've made some things faster. So also be looking out for something that we post on the forums, or the first forums, that we'll probably put this presentation on there and any code that we develop for the beta testing.
All right. As far as last year's code, is this Ryan? Is this connected to the internet? Okay. In order to make it more, making the program more efficient, like when we're making the program, to make the actual making of it more efficient, we have it on our server, and then we get into it through the server. So then that way, if you access it on any of these computers, it's the same program. So we don't have like 10 different versions that are all different, and then it gets confusing. So what we'll do, yeah, we have our own folder too.
Alexander, we have to talk louder than the mall music.
Alright, right now it's just opening our project, and usually once you've put a lot of stuff into the project, it usually takes a little bit longer to open, mostly because there's a lot more stuff to open. Lots of stuff. So okay, wait. Okay. Now, when we made our project, now I'm sure Ryan has already told you that you usually teleop. Has he explained? I don't know what he's explained so far. Has he explained the teleop VI and all the different VIs, what they do?
Yeah.
He did? Okay, so he talked about teleop is where you do your driving and so on. We did things differently. In fact, if you look in our teleop VI, as it takes a while to open, there we go, we have pretty much nothing in it, because it's all done, so we've decided to do it somewhere else. And what we do is we run it in what's the periodic tasks VI, which is, it's a VI that runs separate from main. And I can show this also. Well, I'm going to open several VIs at once. If I open main, periodic tasks is otherwise known as time tasks, runs completely separate from the rest of the main loop. And what happens in here is any task, anything you want done besides driving and so on can be done in here. What we have is, instead of having an Auton have an instance to open the motor and control the motor through Auton, and then have another separate thing for our teleop, is we have one place where the motors are driven. And all that changes is where those motors get, where that VI gets the command from. So I'm not used to the screen share thing. It's, my window is quite, there we go. We have it running in separate loops. So anything the robot does, we have, so like compressor, we have drive itself, getting joystick updates is all in a separate loop, each one. So they're not relying on each other, they can run independently. Now, it's hard to start figuring out where to start. I'd say we can start in joystick. for a joystick, again, when we pull out the values in the joystick, we get from Begin, which is like where normally you always get from the Begin. But typically a team will use, if you go into the palettes, typically a team will use the registry. So you'd put, I don't have anything to point with, but you would usually put like, just the mouse, these lines, the information lines about where it's initialized from would usually go into that registry. And you'd give it a string, a name pretty much, and then you can point out somewhere else. We did it, instead of a registry, we have it all going into a single global variable. And all these get clustered together into a single cluster and goes into what's Robot Global. And pretty much it's a little bit of a mess in here. But everything on the robot that's initialized will go into this single variable. Everything. It's all in one place. And then, back in periodic tasks, whatever we need to pull out, for example, if we want, see that here's Robot Global, if we want to pull out the joysticks, all we have to do is take the variable and then unbundle whatever piece we want. So here we're only unbundling the joysticks. And then we can use this joysticks data to get all the buttons, the axis, whatever you need, whatever you want for driving, operations, whatever. We have two separate ones for operator and driver, of course. Also, different than other teams, instead of like in Taliop where you'd pull out a button and then you'd put it straight into whatever you were operating, we stick it into the events variable, and events is subdivided into different parts. It's like this one's drive, slow down, shooter lid, but it's all part of the same variable. So if I open it, this is where anything event-wise that happens in Robot, any drive, any operation happens here. Now it doesn't know what to do with it. All it knows is you push this button, you put this motor value. It doesn't know what to do with it, but all the information's in one place now.
Can you show where that logic is?
For driving and so on. I was just about to get to that. After it's an event, for actually doing stuff, the first thing we did was actually make it drive. So here, we would pull out the motors. Then, we pull out of events. So if you see this is the same variable. We pull out the power axis, which is just the axis of your joysticks, and we stick it into our drive. And in this little extra case structure right here is to select if you want to be in tank, driver, or arcade drive, which is just what axis you use and depends on the driver, whatever they want. And we have it set up so if the driver pushes a button, this is also from events, it's also another part of pulling on the joystick. If the driver pushes a button for tank drive, it would flip and use the tank drive VI, and then when they're arcade, they can just flip again. Then, after those go in there, the drive value goes into the reference, which it now knows because of Begin. This is the same thing from Begin. It knows where the motor is, and then it drives. That's how it drives. This little extra thing over here is part of network tables. And did you explain network tables? You didn't? Should I bother?
We're getting close to our time, so I don't know how long you want to...
Should I just go through the rest of the program and then if I have time to do that dashboard? Alright. I'll explain this little piece right here in just a little bit. All other events besides driving, so any specialty stuff is all we created on our own. This loop right here is just for shifters. So you want to shift to high gear, low gear. It's got its own loop, and as you see, it's from events.
Hold on for a second. Note, again, data flow. Each one of these loops is running at the same time because we're getting our references and passing them to each loop, and that happens pretty much simultaneously at this point. So we got our global data, we unbundle what we want, and then we pass it to our loop, at which point the loop is going to execute parallel to all the other loops.
And next, we have, this one's actually typically is already part of the code. We just have it in there just because it's the compressor.
Which one is that?
That's the compressor. That always will run. That's part of the frame. Yeah. Anyway, and we have separate loops for different tasks. Like this task, this loop right here, as we commenting is important for if other people look at it so they understand what it is. So you see, this says loop for firing.
How do you put down a comment?
Oh, for putting down comments, just double click any place, and then you can type whatever you want, like I or whatever. When you're done, just click somewhere else, and bam, your comment's done.
And then you can drag that and put it wherever you want.
So yeah, and then you can also delete. Anyway, this loop is just for firing frisbees. And a lot of these loops, especially for the shooting control, some of these loops are dependent on other loops. So, the firing control is relatively simple, but it gets some of its events, but some of these, part of this event cluster is not actually coming from the joystick. Some of it's actually coming from another VI, different VI. And the other VI, if I can close out and get to it, would be, let's see, where is it? Would be the shooter wheel. And we have the two VIs communicating because we don't want to try and fire and the shooter wheel is not on. We want it to only fire if it's actually on, because then if you don't, it can get jammed and so on. So we have it communicating by simply, we have this loop, and this right here was part of what we were doing. We were doing something before, and then we got rid of it, and it was not actually fully unimplemented from the code. We originally were supposed to have different shooting speeds for different heights of the shooter, and that got unimplemented, and it wasn't fully taken out. But as far as shooting goes, you push a button, it would give power, whatever this part of this array is. So, and yeah, it's not, like I said, it's not fully unimplemented. What we have is whatever the height is, and what we have from the joystick control is we're using radio buttons, which is the type of button inputs. Or if you push one button, it selects that button. It's actually it's numeric actually. So
notice here when we went over arrays earlier, that's what we're using here. So our height is telling it what index, based on the height that we select, it changes which index of the array to select for the shooter speed. So you can have one thing driving another. You set the height, and then based on that height, you index or you select an index of your array, and that index is the speed of the shooter wheel that you want.
So, yeah, and also, Richard, these numbers weren't all the same, but they make it making it easy to just quickly, because we were in a rush, we're being pressured because of the pressures of build season. Instead of unimplementing and remaking it to be simple, we just made all of the values pretty much the same. But that's an example of something you can do with arrays. You can index through. Anyway, after you turn on the shooter wheel, this right here rewrites, puts a value, a Boolean value, back into events, and that goes back to what I showed you before, the firing loop. So it's, once it knows, oh, the shooter wheel is on, I can fire, and then it won't fire till you push the button. Fire.
So again, that's demonstrating unbundling that global reference, pulling out a value, updating that value, and then rebundling it back into that same global reference so that it can then be used in other areas of the program.
Other stuff, we used to have a climb sequence because our robot used to be, it was supposed to be a 2-level climber.
What does that look like?
Well, oh yeah, another thing about VIs, you can also make custom
Icons.
custom icons, and you want to try to make the icons at least some hint of what it does, and that's just, it's a little pyramid because we climbed the pyramid. So it's supposed to be a little bit like what it actually did. Originally the sequence was, it would climb arms go up, it would pull itself up, and then it would do a winch. But since that was taken out, it kind of became simple, and then that's like all that's in there. But the VI originally did a lot more stuff, and it was just taken out, and then the VI stayed. So that's like an example of how the code evolved, and some old parts kind of stayed. They didn't get fully taken out.
Anybody have any? I'm sorry.
Yeah.
Anybody have any questions pertaining to last year in Labview? How do you do something in Labview pertaining to the robot project? Any questions? All right, proceed. He's going to keep going because that's what he does. So it is 12 o'clock. If you have to go, feel free to walk out. I want to thank you all for coming. And hopefully this has been good information for you, and you all can use this in your upcoming season. Again, we will send out stuff on the forums, and I don't know if we have your email. I don't know. Jimmy may have your email addresses. We can send you additional data. Again, be looking out for what we post for beta. And well, they can do they're on the team, so they can do the survey. But also, we have surveys here, so if you like to do I can hand those out. And then, thanks again.
Can we thank our speakers?
I think he wants to continue, so beautiful.
All right, I'll just continue it. Anyway, the last VI that actually did anything mechanical on the robot was the shooter high. Yes?
You said you took out some code last year.
Yes.
Why didn't you just, in programming, we could just comment and then the code would still be the way to do that?
Yes. In fact, some of the code actually was disabled and then, but it wasn't actually deleted. In some cases we deleted, in some cases we did disable, which is actually a case. Because if you go into the palette, there's this case right here, and that's diagram disable. Whatever's in the diagram will be disabled, and that's actually used right here. There used to be, in fact, you can see our robot right here. There used to be a lid that would actually come up, come down, but we found, the mechanical team found it useless. So they got rid of it. But the code wasn't deleted, we just disabled it. And then we put a comment saying, disabled because there is no shooter lid. But it wasn't deleted, it's still there. And you can actually, I can still go into this VI, it still exists, it just won't run. So that's one thing you can do, you can disable it, comment it, and say why.
What about stuff inside the VI?
Well, since the VI is technically in the disable, it'll disable whatever's in that VI.
Well, if I wanted to run whatever, let's say I have two different things, can I have something disabled this way?
Like, you mean like, stuff like, okay, so you disable a VI, you mean like the stuff inside it? No, it won't run. Unless there is a case, because I'll go back to Joystick, there is some cases where we make a VI to be used in different VIs. It's just like a useful thing. One of them is we got tired of making toggle stuff for toggling buttons. So we made a VI to do it for us. And what we did for this is how VIs work. In fact, you can see there's two of the same thing right there. Now, normally it's in the properties. You'd have to go to the properties. I can show you that in just a moment. But technically, those would be the same VI. We ran into problems initially that when we would hit this button for recording, I can explain that. We'll get to recording in just a little bit. But we'd hit the button for recording, and then it would somehow toggle this line, and we eventually figured out that these technically are the same VI using the same variables. But we found you can change the properties. If you go here, this is all the stuff, any property of the VI, and you can go to execution, how it will run. And what we're telling it here is we don't want, they're now using separate variables. So if you run a line into one VI, it doesn't affect this. So in that case, if you disable like this VI, this one will still run. It's pretty much two VIs except the same structure.
It's the same logic. You're just pre-allocating. You're pre-allocating memory for that instance of that VI.
Anyway, back to the last VI I did something mechanically on the robot. We had one for shooter height. Now this one, was a mess. I actually cleaned this up a little bit. It was worse before. But it's actually quite interesting because we have it set up. So really the only input is the height, which comes from Joystick, and it's a radio button. So when you push one button, it sets the value as one thing. But if you hit another, it would disable the previous button. And then that goes into an array, and this is like we talked about before about arrays, you can index through it. What we have in the array are these numbers. These numbers are actually servo angles. And that's what we're cycling through. Now because of, when we initially got the design from mechanical about how it was working, it was a little confusing figuring out how to do it, but this is what we came up with. Real quick, just so you can understand why we did what we did, and the mechanical explanation of what it is on the robots. On the shooter lid, we had to control the height of the shooter lid. We had this cylinder, which in programming can either be on or off. That's all it can be. And then the servo, which can be, we can set an angle. That's all we had to control the shooter height. And then for height, what it would be is, this would be down, you move this servo out, and, excuse me as I tell my mom to shut up. You'd move the servo, then you'd put pressure, if I can put this, there we go. You would put pressure of the servo, and it would hit that block, and it would stop at that height. Now to do this with the program and figure out how to do that, what we had is we had it, oops, I just did that, okay. You'd hit a button for a certain height, whatever the number is. It can be, then you can index, let's say we indexed for, let's say 20 degrees. This was actually 20-degree angle, level of the shooter, but see the number's 48, and that's the servo angle, and we'll get into that. And the reason it's 48 is because it'd be level. This right here, we'll notice, hey, we've changed height. The height has now changed. So then it's going to run through this. It's going, okay, our value is not the same as before, and the number is greater than before, and the greater than is just part of making the code faster. That was implemented later, but it's not the same. This would be true. Then it would this would look here and say, okay, it's not 0, so we're not level. It's at some actual height angle. It's not all the way down. So then it's going to run through the sequence. Now, technically, the sequence we consider kind of inefficient form of doing stuff. We prefer now to use state machines, but This was made before he made us do state machines. And then they didn't get changed.
Yeah. So notice again, when we were looking at the Aton default program, how it used the while loops with a stop condition. And I said you can use a state machine or you can use the sequence structure. Here they're using the sequence structure. But you still have the same delay in each one of these state machines to say, hey, run this for a certain amount of time or hold this value for this amount of time before moving on to the next sequence.
Yep. So
again, we're using the sequence structure here to force that data flow.
Anyway, explaining the sequence itself, what the sequence would do is it's going to set the solenoid to forward, and the forward was the shooter would come down. It was just the way that it was wired. So forward is piston would pull down. Then it would set the servo angle to 0, so it would zero out, pull all the way back. So it would make sure that the servo was out of the way so it didn't get caught in something and jam the entire mechanism.
He said then, but there's nothing forcing the data flow to say that it's going to move down and then set the angle to 0. It's really setting the angle to 0 and
yeah, it's doing it in the same time.
It's doing it at the same time.
Excuse my English.
You could force that data flow, but here we're not doing that.
And after it did that, it would move on to the next sequence, which would set the servo angle to whatever it is from the array. And if we want to do a 20-degree angle of the shooter, which would just be like that height, that was our regular shooting angle, it would set the servo to 48 degrees. And then it would move on to the next case, which it would keep the angle of the servo, but then push the shooter back up. So in that case, the servo would get moved to whatever the angle was, and these blocks were offsets. So whatever, do 48 degrees, that would be all the way, that was practically all the way out. Then this would push up and it gets stopped. And that was a height. To change height again, you just push a different button. If we did 45 degrees, it would run the same thing actually, it would run pretty much exactly the same thing. It would come down, the servo would move out to avoid blockage, would move back to a different angle, and then pop up. Now, the extra stuff, this extra case outside it, in this case in here, was to make going to certain angles faster. This one right here was for if your height, if you're going from, let's say, 20 to 40 degrees, then it would run a certain way of doing it. It would go a certain path. But if you're going from, let's say, 45 degrees to 20 degrees, it would run something different. In which that case, it's, because if you see here, the only difference between these, I'll explain, is we have a delay. We had a delay so it would have time, because the solenoid just took forever, and have time to come down and the servo can move. This one does not have a delay. It did it practically as fast as the computer could think. Because we didn't have to worry about it, because of the way it was moving, we didn't have to worry about it getting blocked. So we just had, okay, we don't need the wait, we'll just have it do it instantly, and then the driver was happy, and then he could shoot faster. He'd have an extra second.
Time is critical in a match.
An extra second to shoot. And then this one right here was for this whole case, which for if you're coming all the way down, for if you were going, you usually came all the way down for loading, not for loading,
or
just driving around. It would do it faster. Pretty much all we did was just drop the shooter. We didn't need to do a whole sequence of going up, down, and block.
Where did you get your height? How did you get your height?
The height would come from, we find it. It came from the events, which was updated by Joystick. Actually, and here's the height positions. These are radio buttons. So if I select one, the other one's unselected. And those are controlled by the joystick.
Well, I guess we're saying, how How do you determine the height?
Like, how do you control what height it was going to? We had the driver would push.
I mean, if you're saying degrees, if you wanted to so many degrees, how would you know that you need to put so many degrees?
Oh, like what angle to put the servo at? That was done by pretty much just trial and error.
I was wondering if you had some kind of target system or not, because it would be on top of the
Yeah. Well, mechanically, this robot can only do specifically like 2 different angles because of the fact that it's just a block. So, and then for the servo angles, it was just kind of trial and error. Okay, let's see what angle does this, how far does that little block come out, and just kept trying. Seeing what was right. Eventually, found the 2 degrees, the 2 angles that work best. Yeah. And for controlling that, real quick, I'll just show. The radio buttons are actually numerics. So the change that we just have is so when you hit a button, it sets the numeric value of it, and then it'll get stuck in that position. It'll stay there until you hit a different button. That is mostly it for mechanically what it did, but there's other stuff for like the network tables, which is part of the dashboard. And then there was the Auton, which was very special. It was a great idea, but there was unforeseen problems, but it was a great idea.
We actually have some work to do around that. But, it goes back to what I was discussing when I was talking about loops and determinism. Basically, well, I'll let you explain what we did and then how I think we can probably improve it.
Well, what we did is our Auton was, we called it recording. And in driver terms, what the driver did, I'll explain the code in just a moment. What the driver would do is he would just push a button, and that would activate the recording sequence, and whatever motions he did on the controller will record it into a file. So if he could drive forward, then turn, so on, do whatever, and it would be recorded into a file. Hit the button again, write the file, and it would be saved on the serial. Then when you did Auton, we used the dashboard to select which Auton to run. That's part of network tables, but you'd select which file to run. It would pull that file out, pull out the cluster. It was a cluster, and then play it back. So pretty much whatever he recorded into whatever file they named, you can then play it back in Auton, and it would drive theoretically. Theoretically, it would do exactly what the driver did. Unfortunately, we found it didn't exactly do that, but it was a great idea when we came up with it. Yeah. The writing.
Yeah. So the issue that I think we were having with the record and playback was we would record at a certain rate, and we would want to play back at that same rate, except it was non-deterministic. You could not play it back at the exact same rate that you recorded it in. And so I think that's where using that time structure would probably help more, because we just used the regular while loop to execute that.
Actually,
so if
it's a for loop.
Or a for loop. So if anything else was executing on the robot, or if something took longer to play back than recorded, then you'd be out of sync. And so probably it would work best to implement more determinism or deterministic recording and playback using that time structure.
The other thing we ran into was the problem of interfacing that to work with something that mechanically is not perfect.
Exactly.
Because
they're slacking the drive the chain. Yeah, well, they blame us for plenty of things. So
we found my hypothesis was technically every single time you drive it, it's not the same. literally, like every time you turn it on, it's never going to drive the same, but subconsciously, because it's the human mind driving it, you don't notice. I mean, like, you subconsciously correct for it. But a computer's going to play back literally exactly what was done before, and since every drive's not going to be the same, it's trying to do what it did before, and it's not going to work. And then it gets off, what we found was it would progressively get worse. Like, it'd be off like 1 degree on a single turn, then that screwed up everything else, and every turn was screwed up. So it would progressively get worse.
I think it'd be better to use a sensitive feedback using system to try to control it more.
See, that was one of my ideas to try and...
That would help. But then, again, you run into, okay, driving. Driving was a big thing with this record and playback because we wanted to position ourselves. But if we record on the practice field and then take it to the competition field where it's not the exact same surface, you know. So that, you know, there are variables in that inherently would cause issues.
One thing I could understand when the programmer is guilty is like, they would always say that the member would just say, why can't we take this formula and put it over this field? They can't make the same grade. Why? The formula is right there. It's like, well, if it's the same thing with cookies, you make cookies. And 12 people make it in different ovens, different degrees.
Different product, exactly.
So that's what you're doing. You're taking it from the practice field. The practice field might be an inch option.
Exactly. It may not be level,
Right.
you know. So
Carpet might have
carpet,
a little more friction.
exactly.
Explaining what we did. This is what we did. This is not fixed. This is what we actually ran in competition. And I spent many an hour trying to troubleshoot and get it to work, which was all I came up with was why it didn't work and not what to do with it. Yeah, but usually people who have regular Ontons will use a sensor. The problem was getting the sensor to work with recording. That was the problem. That's what I wanted to work on this year.
And also starting at the same exact position, you know, because you have to move the robot and set it up, configure it, you know, before the Auton starts. You know, you can get close, but it may not be at the perfect angle or the perfect pitch or the perfect coordinates on the field.
You take more complex actions than simple back, forward.
Yeah.
So we compensated by just simplifying it and starting at one stationary and leaving it stationary and shooting from one position versus. But the idea is if you can record, you can do basically whatever you would do in teleop. So, you know, in last year's game, you were allowed to start in front of the, whatever that line was. You could have two discs, but then you could go and retrieve more discs. You know, if you were able to pick up from the floor, then you could do that.
But the other advantage, one of the reasons why we did recording was if you started further back, you touch the back computer, you got 3 discs, remember?
Right.
And then the idea was if you started, well, you could start in the back, get the 3 discs, and then the robot would move forward, and then shoot from a closer angle, so you have a better chance of shooting, and it's got 3 discs.
Almost depending like pick a board, pick a drill, like that.
That was one. We tried doing that. I remember I had Austin record trying to smash into the wall to get it to 0, but
Smash might not get it to 0.
well, he zeroed it with the wall, and then it still
Not
didn't
necessarily smash.
Yes. Anyway, explanation of how this works. What we did was we take from the we were able to do this a lot easier with the fact we had an Events.vi. The way we structured it was a lot easier to do this because then all we had to do was pull out our clusters from the events, it's all in one spot. We can just pull it from one spot, take everything we want to record. So the height, shooter wheel, the fire, the drive axis, with drive mode it's in, take all of it, bundle it into a single cluster, and then build an array out of it. And that you would have an array of this massive cluster, and it would build up. And that would start when you hit the record button. When you hit the record button again, it would run this, and what it would do is it will generate a path just like Windows Explorer will make a path. Then attach record the file into that path and write it, and it becomes just a binary file, and it would record the path usually to the serial. When we were running off the laptop, it usually wrote it to the laptop. We had problems trying to get it to transfer. Eventually found out when we found out the serial didn't communicate in you told us to communicate in the FTP. Yeah. And then we just opened a direct line and then just copied it straight in, just like it was another computer. But that's how it would write the file. And then also, when you start recording again, it would zero out the cluster because the cluster was still there. So then you can record a different file. In order to record multiple files, we had this is the string, the name for it, and that came from the dashboard. In fact, actually, since you have the dashboard open, I might as well show you and explain everything on here. We had an indicator for if it was on, what gear we were in, what tank mode we were in. Most of it, the only thing Austin really used it for was just off time. As you see here, we made this switch. So, and if you look in here, this entire case is connected to CAN record. And you see, this is CAN record. So this, using what's called network table, is able to communicate with the dashboard straight to the robot. And we had this because our driver was afraid that he would accidentally hit the record button in the middle of a competition and then it would erase the file. And then that'd get annoying. So we had this button that's a little safety, so it would be on no, and then when we wanted to record, we'd have to manually hit yes. This indicator is for if it's actually recording, so we don't accidentally think, oh wait, we're not recording. Yeah. This right here is our selector, and this gives a string, a name, and this will go, it goes to two places. One, it goes to here to write the file with that name. And it also went to playback, and I'll show playback in just a moment, so it knew which file to play back to. It was nice because then we could just use this single select, just like, alright, let's record shoot long distance. It was just the name we came up with. Try and explain it.
One question. Do you guys want to make a hard stop at some point, or just keep going? It's kind of up to the audience. Okay, alright, sorry, just checking. Keep going.
Yeah, but think of something.
Alright.
Okay, alright, it's fine.
The nice thing was we can have this single string, and if we want to record, we would hit record and record to that string. And for playing back, it would play back whatever you have selected. So you play that back, play that back, whatever. Anyway, so then back to this, we have a file. Now for playback, that was actually surprisingly not in periodic tasks. It still used, the nice thing was, having this structure, is it actually still uses that VI, the drive VI. It just, we had the playback actually where it was technically supposed to be. We actually had it not on. And that's it. This right here is a VI to grab the path back out, and then read the file, and as you can see, this is the name. Pull out the cluster. Then it would figure out how big, except we found out later we technically need it because of the tunnel, part of Labview.
So again, with the enable indexing on the for loop, you can either wire the in, or you could wire or enable the indexing on this node. We did both. So.
Yeah, I didn't know about the tunneling, so I put this in there, and it's like, oh, this does it automatically. Oh well. Anyway, and then once in there, it would open the cluster, and then send all the values back into, it would write back into events. And then this right here just controlled how fast it would do that. And we had the recording in order to try and get it right. It would record at every frame being 50 milliseconds, and then it would play back at the same speed. That was the first thing when we first saw it not working. That was the first thing we started toying around with to see if different numeric values to try and get it right. But we found by slowing it down, by making it, because it used to be 20 milliseconds, by making it 50, it worked. It worked a little bit better, but it still didn't get perfect.
I wonder if you could incorporate more features feedback. Like if you had a bunch of little sensors that would detect, like when the arm would go on this far, or when something could turn this far, and like check, every X execution. So how are these two? Have you crossed the path of the sensor?
Yeah, and that's the thing about using time as a limit. It's really dependent upon the CPU in those clock cycles to say, hey, yeah, you reached the time, but 1 second and 1.02 seconds are not the same.
Now, if you reach the target system, you can use automatic.
Yeah. Well, we did.
Yeah, we've used. We might have even had a gyro on this robot.
We did, and then they took it off, and then they lost it.
So you can so for driving in years past, we've used the gyro to say, okay, turn to this angle, and then drive straight. We do like a sort of not a PID, but just a P loop to say, okay, drive and stay at 0 so that we can drive straight in our time, something like that.
See, we did it. Initially we kind of didn't like this, even though we didn't have feedback, mostly because it was a new idea of you could change the Auton after building. You didn't have to go back and reprogram and then rebuild it and then reinitialize it. You could do this and just take the robot. Let's make a new Auton.
This was the first time that we've done this, so we have yet to perfect it and make it work better. So.
And yeah, this thing, if you're wondering, that was just a timer. That was part of our debugging too. And one of our controls people was a little nuts, so we decided to name it a little weird. So
in the robot project, if you can bring that up, just bring up the project. Under support code, this elapsed time, what you can use that for is to check how often a VI is running. Okay, so